Uh, Good afternoon. It is a great pleasure for me to present Julio Rebelo from the University of Toulouse, and he will talk about approximation on the circle.
Thank you, Laura.
Thank you.
So many thanks to the organizers for the invitation. I'm very happy to be back at IMPA and to participate in the conference for Frank's birthday. So congratulations, Frank, and many happy returns. So my talk would be is intended to reveal some dynamical issues involving groups acting on the circle, groups of diffeomorphisms acting on the circle. And if I'm fast enough, I'll be able to at least state a recent result that I'm actually very happy with this result because it sort of removes from the back of my mind something that has been hanging around for many years. But I mean, at some point, I considered to give a sort of more conventional talk directly about this. But you know, probably as we grow older, we start like having more appreciation for storytelling and everything. So I decided, so if I go straight into this thing, I won't be able to actually convey a lot of important information, and in particular not to explain what was really the issue that has bothered me for so long. So I'm going to go like the easy way and hope that in the end we are able to convey something new as well. So the starting point for me is going to be a paper by Etienne Gis, dating back from 1993. And in this paper, he actually studied, sort of an attempt at beginning the study of diffeomorphism groups admitting a generating set close to the identity. So let's say with a generating set close to the identity. So there's right away, right from the beginning, an issue what close to the identity means. I'll leave it kind of loose, but it's really not a big issue because you can give explicit neighborhood of the identity and say, okay, it's close if you have a generating set that sits inside this neighborhood. And the neighborhood is explicitly described by constants. So this is a minor issue. There's also a relatively minor issue that I will kind of be loose about, that is the topology, in which topology is this neighborhood. Sometimes I will require more regularity, sometimes less. Again, this is minor thing, like anything that you can prove, any assumption, regularity assumption, that you want to use that does not make the problem trivial right from the beginning, it's fine. Any result, any non-trivial result obtained in this setting would be considered interesting. No, as George was saying this morning, when you go into storytelling and motivation, we actually convey our own perception of things. So I will try to convey what I believe to be Etienne Gis' motivations in this paper. And I think he was mainly motivated by three things. There was a survey article by Dambra and Gromov that discussed dynamics of rigid transformation groups. And in the last section of it, it goes like full in. Okay, basically how much the dynamics of a finitely generated group of diffeomorphisms look alike. I mean, not even the dynamics, actually go more into the structure of the group. How much a group that is realized as a group of diffeomorphisms of a compact manifold looks like a linear group. And he actually stated a few questions. Another motivation would be the classical Zassenhaus lemma, and I will remember what was it very soon. And by the way, Zassenhaus lemma is already quoted in this very section. And the third motivation that is much less known to non-specialists is Dominique's theorem. There's a reason why this is not very well known. It's because it was unpublished. And that's back to early 80s, I guess. Early 80s. And what might surprise some of you guys that are more experts is that what about Shcherbakov-Nakai theory? And I really don't think. I will say a few words about this, and then this might actually give here my first line. I don't really think this was a major motivation for him. I think this was a kind of a side thing that he sort of saw, like, an indication that the problems that he was involved with were pertinent. Well, I'll get to this point later. Let me remind you what is Zassenhaus lemma, and this should be actually clarify what is this role of different why groups that admit a generating set close to the identity might have a dynamics that is something of special. So, and again, Dambre and Gromov were more like about, close to the identity or not, we don't care. They were more like into the algebraic structure of the group. But people have different backgrounds, so why not do dynamics? Okay, so Zassenhaus lemma. Technically, you have a Lie group. So G is Lie group, honest finite dimensional Lie group. And if you want, you can think of PSL2R that actually does a favor of acting on the circle. So this is a natural source of examples. And given this Lie group, there exists some neighborhood of the identity. So identity sits inside. The neighborhood can be explicitly described once you fix like a Riemannian metric or something, with the following property, such that if gamma is generated by a finite number of elements lying into U, and there's a minor assumption here that gamma is non-nilpotent, which basically means is sufficiently non-commutative, then gamma is non-discrete. Non-discrete means what? Means simply so there is a sequence, say, Aj of elements in gamma, a non-trivial sequence actually, so every Aj is different from the identity, and such that Aj converges to the identity. So this definition of non-discreteness, non-discrete group, Means obviously, like, you are in a Lie group, you simply look at the points. I mean, you see the elements of the group as point in the Lie group. The Lie group is a manifold itself, so it makes sense. So in the end, you are asking, I mean, is this set, this countable set of points, a discrete set or not? The issue is being non-discrete is extremely powerful, dynamically speaking, in this set. Because if it's non-discrete, I take gamma bar, I take its closure in the Lie group. And the closure, and gamma bar is closed by definition, because just take the closure. And the closed subgroup of a Lie group is itself a Lie group. So this thing is a Lie group. Is a Lie group that actually is non-discrete. So it does have a non-trivial Lie algebra. So if these things, if G is acting, you can think of PSL2R. The group is acting on S1. And if you pick a subgroup of PSL2R in this condition, you look at its closure, you look at its dynamics, gamma. Here. Gamma acts on the circle, but gamma bar has non-trivial Lie algebra. So this non-trivial Lie algebra gets represented in a vector field on S1. And this vector field, and the dynamics of this vector field, just like I flow everything on S1 by X, and this dynamic is the limit of actual elements, of the dynamics of actual elements of gamma. For every T I fix, so for every T fix, the map phi xt is the limit of actual maps in gamma. And the limit is like, whatever topology you want. In particular, like, in this case, you cannot have like a counter set that is invariant by gamma. Because, you just like drag everything together with the vector field, and there's no way the counter set can survive. As a complementary remark in this setting, I can give you a simple example to show that the assumption close to the identity is obviously really important. But I mean, this example, simple as it is, it has different motivations. You can actually do it in PSL2R. You take an element, you take a south pole, north pole diffeomorphism like this, F. And you take same thing by rotated by over pi over 2, say like this. So east pole, west pole to east pole or something like that. Say G. And you arrange, since they are in PSL2R, I can see then their extension to the disk. And you arrange, you have one parameter family of maps doing this and one parameter family of mapping doing this. So playing with the parameters, you can arrange to have this picture. So this is F, this is step 1F, is taking this geodesic to this one. And I arrange for G to take a geodesic like this to a geodesic like that. So that I get this, this kind of quadrilateral, but with a hole in it. Well, it's like, a holed torus, not a punctured torus. If you look at the dynamics generated by F and G, so this gamma is rank 2 free, means the fundamental group of the punctured torus. So it's free is F2, free on two generators. And the dynamics. I won't try to make a decent picture, but as you repeat this picture, you start like removing open sets from S1, like small intervals. And what remains is a counter set and is invariant. So gamma has a minimal set minimal invariant, of course, set that is a counter set. So funny dynamical phenomenon, very studied in Kleinian groups, discrete groups, and everything else. But something that cannot be produced close to the identity if you are in a Lie group. So this is the main motivation of Etienne Gis, I guess. And he's like, okay, is it true that something like this might still hold if you simply do not assume you are in a Lie group? So what were the evidences? So I didn't say yet what was the Dominique theorem. Dominique theorem comes first here. So Dominique's theorem says, yeah, well, kind of yes, at least topologically. If you are close to the identity in the C2 topologies. Dominique's theorem is the older result in this direction. Dominique. So there is a C2, but I mean, as I said, topology, I'm not paying much importance to topology today. C2 neighborhood of identity such that if G of gamma is generated by elements in U, then gamma is minimal. That is, all the orbits are dense unless it has a finite orbit. That's to say, it's really equivalent. There's no invariant counter set. U is the neighborhood. There is such a neighborhood U. Okay? Again, it's explicit. Well, I mean, from the very moment Dominique proved this theorem, there was the question about its metric analog. Like, would a group like this, like a minimal group like this, be ergodic with respect to the Lebesgue measuring? Like, that's to say, is it true that every Borelian, so is gamma ergodic with respect to Lebesgue? That's to say that if whether or not every Borel set that is invariant by gamma would have null or full measuring, Lebesgue measuring. All right. So this question was open by then. And what Gis did in his paper? A number of things, but I mean, as much as the circle is concerned, he was able to make accurate the brief mention to Zassenhaus lemma in Damber-Gromov. I mean, there's a remark like, well, it seems like, if you start close to the identity and you iterate commutators, these commutators, you converge to the identity. So who was able to do this? So again, there is some neighborhood of the identity and they changed the topology, but I mean, I don't pay much attention to this anyway. Such that if, let's say this way, if F1, F2 are in U, then the commutator of F1, F2 is not only U, but is actually closer to the identity than the initial ones. And then you have the natural idea, okay, what about I start iterating commutators? I'm getting closer and closer to the identity, so I'm producing something non-discrete, unless, of course, all those commutators, I mean, at some point, they degenerate into the identity. So which he managed to prove was not the case, provided that gamma is non-solvable, which is a really very weak assumptions, almost no assumptions. It's like, no, you're not dealing with the two small groups. As a consequence of this, he was able to get a sharper version of Dominique's theorem, the analyte with more regularity, but sort of sharper because in the case there is a finite orbit, he was able to say, okay, in the invariant intervals, all orbits are going to be dense anyway. And that's very much where I picked the problem. Let's put it this way. So what was the state of things for diff C0? So the moment I have this thing from one hand, and from the other hand, I have the Cherenkov-Nakai theorem. That does, that deals with this almost the same thing, except that things are not globally defined. There will be a big issue about being globally defined and being locally defined, being global or being local. And this is very much what has bothered me all along. So they actually get here a non-solvable subgroup. Non-solvable. And they manage to construct flows. So there are vector fields. That really imitate what the vector field in the closure of a Lie group or Lie subgroup does for the dynamics. So these vector fields are defined, and whenever you get some set, some open set, and some t such that the flow of x at time t is defined on U, then this map is limit of maps in the group. This is tremendously important statement that clarifies the dynamics. There has been many applications. I shouldn't have written there, the definition there. Okay, we erase it. We would have Béliard, Lewis, Loray. That would prove, that would pick high vector fields, elaborate on them, and prove that you can basically whatever germ of map you are given in the beginning, holomorphic map, of course, it has to be holomorphic, then you can approximate them by elements of the group. So in the sense, this group is dense. So we put between quotes, gamma is dense in diff C0. Well, not really dense, but almost. Actually, it would be C0 without the origin. Those things are not defined on a neighborhood of the origin. All right. So one of the possibly an additional motivation was that if you construct these vector fields in the circle, you would be able to use them, for example, to settle the question about ergodicity. Okay, so let's say you mark Sherbakov-Nakai vector fields on the circle would settle its ergodicity of groups. There's, as I said, I think that's the moment I have to be kind of explicit about this. There is this issue which permeates basically all of the story about being global and about being local. Local versus global. So our maps are in a sense global. Even in this case, which is eminently a local setting, you can still think, okay, it's global if it's defined on a neighborhood of the origin. And in the circle, of course, if you start like groups with the heterogeneous groups, the maps are converging to the identity over all of the circle. But still, you are doing very nonlinear dynamics. So, behavior of the dynamics in regions might differ, in different regions might actually differ deeply. So it might be a point, there might be a point at looking at, a local aspect, really. I'm looking at this open set, that open set, and seeing what happens. Sherbakov-Nakai vector fields, even in this setting, they are local already. They are local in the sense, as I said, they are not defined on a neighborhood of the origin. They are defined in sets, like, that look like sectors. They are here defined, holomorphic, and they have nice asymptotic properties at 0. But they cannot be defined on a neighborhood of the origin. All right, so what happened next? At some point, I managed to construct these vector fields on the circle. The difficulty was basically that, I could dream of a global vector field. Or I could localize the problem and say, all right, I don't know how to construct a global vector field, and I don't know whether or not it exists. But I can consider some interval, no empty open interval. And consider this pseudo group given by restrictions of gamma. Well, even if gamma is global, there is nothing that prevents me from considering gamma the pseudo group on I yielded by restrictions of maps or generated by the generators of G. Induced. Well, gamma was my group, so gamma is not an excellent idea. Let's call gamma sub I. It's not brilliant, but it is what I can come up with. Induced by gamma. All right. So from this more local perspective, the difficulty compared to Nakai, Shcherbakov-Nakai, was the common fixed point. Those guys, there are two maps at least, because the group is non-solvable, non-commutative, very non-commutative in a sense, and they share a fixed point at the origin, which is no longer true on the circle. There are elements with fixed point, yes, surely, but fixed point will not be common. The stabilizers are going to be cyclic, homogeneous. So this thing I managed to do at some point. There are SCN type vector fields on S1. It's really locally construction. All right, so there where the issue started for me. I was only able to produce vector fields that were locally defined, although my group was globally defined. So the problem about is there like global vector fields, whether or not they exist, has always been boring. You can assume real analytic. The G's theorem is real analytic, but convergence you don't need to assume it's real analytic. The convergence and the regularity are relatively minor issues in the story. Then, I should continue my list. Then I met Frank, and as I told you the day before yesterday, he helped me to understand foliations. That's where, I started doing foliations, at least holomorphic foliations. My original background from graduate school is indeed more like real dynamical systems. Frank was, we got involved in trying to do this, some version of Nakai vector fields, and if Cn 0, well, whether or not 0. 0 in the first moment, and then you might think, okay, you perturb, you keep your vector fields, and you get rid of the fixed point, of the common fixed point. And actually, Frank also removed, the monkey in my back about this local and global thing when he told me of a result, an example, I think. Well, it's presented as an example in an article, if I'm not mistaken, by Berthier, Cerveau, and Neto, that noted, you'll get here. So they regarded the two local diffeomorphisms, to Z and Z, Z square, and realized and proved that the group generated by these two maps is to begin with 3 on 2 generators. And has the remarkable property that the Taylor series of any element in this group has integral coefficients. So that's to say, Nakai vector fields for a group like this, the chi-vector fields are defined where they are, and they cannot be defined. There's no a better theory that would yield vector fields defined on a neighborhood of the origin. So I was extremely happy when I learned this, and I said, okay, forget about the global thing on the circle. Albeit I didn't have an explicit example, you could guess, okay, just like, get some finite orbit and give yourself a little bit of work to produce a similar example. All right.
Sorry, but do you have an example of the circle of this kind? Globally discrete, but not locally.
No, I don't. This is one of the questions. We have fought in the past a bit. Locally discrete, no, globally discrete, but locally non-discrete. I don't have this example. This is one of the questions I might ask. I was planning to ask at the end. All right, so where I was, I kind of, this is Loray and me, and kind of, funnily enough, when I look back now, is that when I did this thing here for the first time, I used the method, the simple method, which is somehow similar to what is used here, but is at the same time is different. In that, I was really using the circle, like a real one-dimensional thing. And when you did this thing here was different thing, and the method was essentially different. And it was much simpler. It was a lot simpler and a lot more efficient. So that I don't think anyone actually ever noticed that the proof that I have given in the circle before was slightly different. And this actually is the key point to get the global statement if I have time to state it. It was one of the key points. There are two key points. All right, so with these local vector fields here, you could do basically everything that you would like, that at least I would like back in that time. Let me try to figure out how much time I have spent so far, about 37 minutes.
You have until 50.
15?
No.
No, I have until 50. Okay, I have like 15 minutes. Okay, shivering a bit. There was later there was an independent sequence of works that attracted my attention on the circle that are, basically the paper that I know better, the paper that started the trend, is Bertrand, Klepsin, and Navas. And in this paper, they proved many things. And they proved in particular, how can I introduce it quickly enough? One of the main theorems here is that get a group acting on the circle that has no finite orbit. And, slightly more general than this, assume there is no invariant Majory. Invariant Majory in this setting is basically almost as good as finite orbit. Invariant probability, indeed. Finite orbit can be interpreted as invariant probability, that it unless you are really in this case of finite orbit, the invariant probability will not exist. And it has nothing to do with close or not being close to the identity. It's a general statement, very general statement. Then there's a unique stationary measure. So what a stationary measure is? I would like, the principle is, I would like to do ergodic theory for groups acting on the circle, in this case. The very basic of what I would call standard ergodic theory, like you learn in most books about ergodic theory, like short like this, is that every self-map of a compact matrixable space has invariant probabilities. And this fails miserably once you move to a group. For example, the example I gave earlier, the group like this, like this F, and then you get G, which does the same thing but going east to west. This group has no invariant probability, because what are the invariant probabilities of F? Points, there's the support of invariant probability has to be recurrent, has to be contained in the set of recurrent points. But F is wandering, unless you are in the South Pole or in the North Pole. So the only invariant probabilities for F are convex combinations of atomic measures centered in the North Pole or in the South Pole. I mean, same thing works here, like East Pole, West Pole, and there's not a single one that's common. So a stationary measure comes like a replacement. Okay, let's ask less instead of asking a measure to be invariant. Let's just ask that its average, it's invariant. So I try to put the definition. So the definition is, okay, you have to give yourself a way to do averages. So you give yourself a measure on your group. Let's call nu. On the group, an honest measure that actually sees the entire group. The support generates the entire group. And then you say that mu is stationary. And the stationary is relative to the fixed nu. If mu of a Borel set is the average over the group of mu of the element of the group itself, nu of the element of the group, mu, the gamma minus 1 of the Borel set in question. So this is the definition of stationary measure, and they have the major advantage that they basically always exist. What is remarkable here is that they are unique. And in this paper, they proved many theorems that would actually kind of help me. So, okay, 5 minutes about it. I got interested, I learned, I mean, they carried on with various co-authors to actually get almost a totally complete, as far as I understand, classification of what would be called the locally discrete groups. So basically, the assumption I needed, the assumption I said in the beginning, I could localize it, the non-discreteness. And this, this class of this group, the group is large, for example, because of G's theorem in the beginning, but it's actually much enormous. It's really so large that, the Juan-Klebs in Avas, and really I want to try to list all the collaborators. There are many that that play their role there. They essentially classified all the complement of this, I mean, all locally discrete groups. The paper that I really think I understand well of them is this one. The others I understand much less well, or almost not at all. And then, at some point, there was a turning point. I said I was extremely happy when Frank showed me the example by by Berthier, Cerveau, and Neto. Because, I said, okay, I can forget about global vector fields and stuff. And then Bertrand once come to me and was like, there should exist a global vector field. Maybe remove the assumption of having finite orbit, put it slightly more general, and would there be a global vector field? And I was having nothing of it. I was, no. I mean, I got a monkey out of my back. Don't bring it back. But at some point, I mentioned this to Helena. And Helena, she would probably put it herself, doesn't buy anything that is not on sale, and indeed heavily discounted. So I wasn't buying Bertrand, but she wouldn't be buying neither Bertrand nor me. And then she actually said, okay, why you are so sure the statement is not true? And then we started discussing. Now, I was trying to give her a price to buy me. I was trying to sell myself to her. Okay, you shouldn't believe in this thing. And as we discussed, we basically end up proving that Bertrand was right all along. So this statement, we actually proved. It's, you still removed the monkey. I mean, you didn't bring the monkey back. You might start with the question you asked before, but I mean, it doesn't kind of needle me as much as the previous one did. The statement is like follows. As it is now, I mean, it's still not fully written, but it's not really complicated. It's really not very technical. It's surprisingly simple in a sense. A theorem. Of course, you have to assume that the group is globally non-discrete. So, to make it simple, let gamma be as in G's theorem from the beginning. Or from above. Then there is a vector field X defined on all of S1 and whose flow, every map induced by the flow, time T map induced by the flow, is limit of elements in gamma. So the limit here, as it is now, is C1. C1, it works. I don't know if it can be done better. But this is really good enough. The conclusion, I will finish in, 2 minutes. Is it okay, Laura, if I finish in 2 minutes? Why did I mention stationary measures? Because one of the things that were in the back of my mind here, since this paper, was before I start thinking about the stationary measures, I used to say, I don't know of any problem about dynamics of group on the circle that I can solve with a global vector field, and I cannot approach with the local ones. Of course, global think is a more aesthetical thing. Technically, you simplify a lot of issues, but I mean, the problem remains at least approachable. That was like, my psychological trick to keep the monkey away. The existence of stationary measuring really is this problem. Or more precisely, a major result due to Furstenberg actually, for discrete subgroups of Lie groups, is that you can get a stationary measuring that is absolutely continuous. And the problem about the regularity of the stationary measuring is absolutely fundamental. If you can get results in this direction, it's absolutely fundamental. So what was clear at some point, related to the thesis of my former student, Anna Zeskith, was that I would be able to prove the existence of an absolutely continuous stationary measuring if I have a global flow. But I mean, with the local ones, it looked at least very challenging. I really still don't know whether or not it's true. Maybe it is, but I mean, I wasn't careful enough. So a sort of corollary of this theorem is that this group gamma, I can give a distribution of weights to the elements of gamma, and whose support is in general infinite, that will yield a stationary measuring necessarily unique, but also absolutely continuous. Okay? I'm running out of time, so I think I will stop here. There was a few additional things that I would like to tell you, but you can forget. One of the things was the question that Bertrand already asked. Is it true? I mean, how can you produce groups, examples of groups that are locally non-discrete, that are globally discrete? This I don't know. All right, I'll stop here.
Thank you.